Hi physics class, today we're going to learn about Hooke's law, which we'll spend a few days on. By the end of the week we'll have our unit assignment, and things are looking good. Weather should warm up. I hope you're enjoying it. Alright, so Hooke's law involves springs. Back in 1676, Robert Hooke formulated the relationship between the force pulling on a spring and the amount a spring stretched. He determined it was a linear relationship, which isn't exactly earth-shattering. Basically, if you double the force on a spring, it stretches twice as far. All right. So a graph of force versus displacement of the spring would look like this. There's never a y-intercept, and I think that should make sense. I should say the y-intercept equals 0, and that should make sense because if there is no force acting on the spring, there's no displacement. Okay. Let's talk about the slope. The slope of this graph, I'll remind you about your grade 10 linear relations, y equals mx plus b, m's the slope, b's the y-intercept. We already know the y-intercept 0 for all force displacement graphs of a spring. The slope of this graph is called k, and it's called spring constant, or sometimes you might hear it called elastic constant. Okay, and every spring has a different spring constant. A high value of k means it takes a great deal of force to stretch or compress it. A low value of k means it doesn't take much force. Okay, so I've kind of contrasted them here. Okay, so that's what their graphs could look like. A low value of k could be like a little toy spring, or a spring in a toy, or a slinky, say. A high value of k could be in the suspension of your vehicle. I hope that makes a bit of sense. Okay. One thing I'll definitely ask you to do is to determine a spring constant from a graph. So I've labeled this graph. Always pay close attention to the units. Force is in newtons. The displacement is in centimeters. Okay, so we've got this behavior here. I've intended to line it up when the displacement's 14 centimeters. The force was 5 newtons. Okay, so to find the spring constant k, it's just the slope of this graph. Okay. These graphs always go through the origin, so they're really, really simple. The rise is just going to be 5 newtons. And the run here is 14 centimeters. I'm going to go ahead and put that into meters. Okay. When I do this calculation, I get 35.7. The units of spring constant, typically newtons per meter. That's all. There's no special name for that. What it's saying for this spring, it would take 35.7 newtons to stretch it by 1 meter. It's the same behavior if you're compressing a spring. Some springs are designed to do that. So it'll be 35.7 newtons required to compress it.